Okay, the next topic in this class, new topic, is cables and pulleys. And you are familiar with cables, and I will talk about pulleys, but a few basic facts about this subject matter is, first of all, we know that cables can resist tension only. We know this, cable like a rope, if you push on a cable, if you push on a rope, it does not resist. So in other words, it cannot take compression. It can take only tension. Unlike a truss member can take both tension and compression. So how's this going to impact our analyses here? Well, if we ever get a negative, if we show tension on our free body diagram, which we will do, and we ever get a negative number, we know the system is unstable, that it can't really, the cable cannot take that compression, so we've either made a mistake or the system is unstable. Okay, so the other thing is the tension in a single cable, even as it wraps around a frictionless pulley, is the same or constant. So in other words, here is a pulley, and here I have a single cable wrapping around that pulley. It's one cable. In other words, I can follow it here. It goes from the weight around the pulley to the person holding it down. Well, the tension in this region is the same as the tension in this region. That's if we have, a pulley that has no friction in it, so it doesn't resist anything. It's a little bit of an ideal situation, but if we have a very good pulley, it should be close to being approximately the same. So we're going to use it the same. So if I have a single cable wrapping around a pulley, could go around 2 pulleys, could go around 3 pulleys, doesn't matter. Along that one cable, we are going to take that the tension everywhere is the same. Unlike this problem over here, where I have more than one cable. In other words, the way that I'm showing this, I have a cable that goes from there to there. I've got a cable that goes from there to there, and I have a cable that goes down here. So here I have cable 1, cable 2, and cable 3. So I have 3 cables in this problem. 1, 2, 3. Whereas here I just have 1 that goes around the pulley. So you have to look at the problems and count the number of cables you have. These become a little bit like truss members in a sense. They're connected at a node. In these problems we'll consider weight. So our truss problems didn't have weight. So we're going to add a little complication to these in a sense. Okay, so here's an example, and I have 2 weights here, and I have 2 cables. I have a cable here, a cable there. So a cable, an AB and a BC. And the question is to find the tensions in both cables. So the solution is, and we have the weights here, 12 kips, 8 kips, and again we're going to make free body diagrams. I'm going to start with making this particular free body diagram right here, and again, how do I do that? I use a copy and paste. So I go copy, paste, and there it is right there. Again, I copy exactly what's there. Now I have that 12. So when I look at my forces, though, what do I see? I see that I have, this is 12 kips. So now I have to draw a load that is not really shown. I've got to draw that 12 kips. And then I made a cut right there. That means I have to put a force, or forces. In this case, it's a force. And it's the tension in that cable. So it's going to be TBC. That gives me, well, now I'm just going to erase it, but because that gives me this free body diagram. And then what do? I take a look at that. I take the sum of the forces in the y direction equals 0. Upward positive, so I have TBC, positive because it's upward. 12 is negative because it's downward. Set that equal to 0. I get that TBC equals 12 kips, which of course means it's tension. It is tension. So then my final free body diagram looks like that. And it's pretty straightforward, pretty easy. I take another free body diagram here. Again, what do? I do my copy and paste. Looks like that. Copy, paste. Again, I get my free body diagram that looks like that. And again, I have to add my weights on here. So it shows 12 kips. So I draw there's 12 kips there. And then I have 8 kips. I have 8 kips there. And then I made a cut at my cable there, so I have to write a force, so that's going to be TAB. Again, that's how I develop that free body diagram. It's very straightforward, and I end up with this free body diagram. I take the sum of the forces in the y direction equals 0 again, and I have the TAB positive, the 8 negative, the 12 negative, and I set all that equal to 0, and I get TAB equals 20 kips. Now notice there's another free body diagram, so here's an alternative solution. I can take the same free body diagram here, and I get my 12 kips. For my TBC, that gives me this final free body diagram, but now I could take this free body diagram, and again here, just to illustrate it, I do my copy and paste. When I draw that free body diagram, copy paste, here it is. Well, what's happened? I've made 2 cuts. I've made 2 cuts in this free body diagram. In other words, I made a cut there and I made a cut there. So I have to show forces in both of them. And there's also tension. So first I'll put in the weight, which is 8 kips. And then I have to have a tension there and a tension here. Tension is away from the body. So I have to be, the fact that this is going down means nothing. It just means it's tension. So we have to follow our rules. Now, we've already determined that, that the tension in TBC, is 12. So I can put that right in there. So I already know, I can either write it as TBC, or I could just say that's 12 kips, because I've already determined what it is. It's already given there. So, however we want to show it. So that is illustrated right here. I know that I could write this out straight from this. I've got TAB minus 8 because it's going down, minus 8, minus TBC because it's going down. Then replace the TBC with 12 kips, and then I can solve it. and I get TAB is 20 kips. So I get the same answer. Either way of solving these is fine. Let's look at this one again. I have 3 cables, 1, 2, 3, which is our first problem that we looked at. And I want to determine find the tension in each cable. I have A, B, A, C, A, D. So now it should be obvious to you that the tension in AD, TAD, is 4 kilonewtons. I think you can see that at this point. Because I could take that free body diagram here, and I've got 4 kilonewtons going down, and I have TAD going up, and so I end up with, you can see it, TAD is 4 kilonewtons. So we're going to sort of skip that step. Something that's going to be that obvious. We're just going to, you can see that. So what I'm going to do is I'm going to take my free body diagram about this point. It's going to look a lot like what we had for trusses. So I have the 4 kilonewtons going, so there's my free body diagram here. We've done enough of these that you can see that I'm going to have the 4 kilonewtons going down, and then I have my TAC. It looks just like what we would do if it were a truss. TAC going upward that way, upward to the right. I have TAB going upward to the left, and I'm now going to work with this free body diagram, which we've done. We're going to convert it to this. Again, we have our angles with respect to the x-axis, the 30 and 20. Using simple geometry, we know that those angles here, that's going to be 30 degrees, and that's going to be 20 degrees. So using basic geometry, we know that. So this is upward to the left. So I have upward to the left. And then I use, for the y direction, it's sine of 20 degrees. For the x direction, it's cosine 20 degrees. This is upward to the right. So upward to the right. And the x is cosine 30 degrees. The y is sine 30 degrees. So I look at this, and again, I take the sum of the forces in the y direction equals 0, so I look only at the y ones and put them into this equation. You can all do that at this point, and here are my cosines and sines values. I put those in there. Then I take the sum of the forces in the x direction, where I use these two. Put them in there. Again, I have 2 equations, 2 unknowns we can solve. And we get that TAB, TAC are these numbers, 4.51 and 4.92 kilonewtons. So it's solving that same problem that we did for trusses. Let's do the same problem, but let's shrink the angles a little bit. Let's make it 10 and 15 degrees instead of, what was it before? It was 20 and 30, so I've cut those angles in half. Okay, so why don't you work that problem? You work this problem. This is homework. You work this problem. Okay, so pause the video, work this one. Should be straightforward. Okay, so same thing, except my angles are 10 and 15, and so I'm working with cosine 10, sine 10, cosine 15, sine 15. I put them into my, I convert it to that, and using just my y components, I get this equation. Using my x components, I get this equation. Again, 2 equations, 2 unknowns. I get these values. Now it's 9.13, 9.31. So what I want you to sort of observe here is, at these angles, we're talking about 4.5, 4.92. as I make the angle smaller, what happens? It goes up, and it goes from 4.5 approximately and 5 to almost 10 for those two. So as these angles get shallower, the tension goes up. And if I do it, now I'm going to shrink it I'm going to put these both at 3 degrees. That simplifies our problem a little bit. So I want you to do this one. It's now at 3 degrees. Both of them are at 3. That'll give you an easier solution here. So pause the video and do that. So now I have these are both 3. I only have to do the cosine 3 and sine of 3. And I get, similar free body diagram here to work with. I take my y's, I get that. Gives me that equation. Take the x's. Gives me this equation. And now I can make, when I look at this equation, what do I find? I find that TAB and TAC are equal, okay, because this is now a symmetric problem, so because they're both 3 degrees. So once I realize that TAB and TAC are equal, then I can take that information and, depending on which one, cross that off, put TAB in there, and solve for TAB. So that's easy enough, and then I know that TAB and TAC are equal. So in this particular case, it's a very simple solution to these two equations, two unknowns, because TAB and TAC are equal. So now I get 38.24 kilonewtons. So I've gone from 4 kilonewtons, 4.5 kilonewtons to 38 kilonewtons as the tension in these cables, as what happens, as in a sense this gets flatter and flatter. In other words, as this sort of becomes more and more horizontal, the number goes up. Let's do it, so I'll give you this homework problem now. It's 2 degrees. So do that one real quickly so pause it. Again, you should be able to solve this one real quickly because now, again, TAB and TAC are equal. So go ahead and do that. Okay, what's the answer? Well, again, we don't have to draw it out so much because we just get this equation where TAB and TAC are equal, and using our sines and cosines of our angles. I guess we only really need to use the sine in this case because the cosines tell us that TAB and TAC are equal. So now we get 57.3 kilonewtons. So from going from 3 degrees to 2 degrees, what's happened? It's gone from 38 now to 57.3. And then let's take it one more step. Let's take it to 1 degree. So do this one real quickly. It's obviously, so what I want you to do is imitate this equation. But now you're going to use the sine of 1 degree. So all you have to do is just change this equation for 1 degree instead of 2 degrees. It should take you about 2 minutes. So what do you get for 1 degree? Well, there's my answer. I get 114.6. So now now notice, the tension in this cable is 114.6 kilonewtons. We're only holding up 4. So we have to have a cable that can handle 114.6 kilonewtons to support just 4 kilonewtons when we want to make this very flat, in a sense, horizontal. We're getting closer to being horizontal when we only have 1 degree. So as the top cables get more and more flat, the cable tension rises enormously. We have to recognize this, and we cannot get it perfectly flat. Because we can't get it perfectly flat because there would be no it can't be like this with a 4 kilonewtons going down, because there's no vertical component here. There's got to be some little vertical component going like that, so we cannot make it perfectly flat. It's impossible. And but as we try to make it more and more flat, the tension goes up and up. So like I say, the cable tension's 114.6, but we're only trying to hold 4 kilonewtons. So it's, a factor of almost 30. Yeah, 30 approximately. So we have to have our cable. Okay, so there's a lesson to that. What is it? So in other words, if I try to, if I'm trying to hold up 4 kilonewtons on a flat, telephone line or whatever you want to call it, utility line, and I'm holding it up by 2 poles, what's going to happen? Well, there's tremendous horizontal forces here, 114 kilonewtons. What's going to happen? Well, we're going to get tilting of the poles and that sort of thing. So as we try to make things more and more horizontal, it increases the load on these poles in a sense. So that is the moral. We're going to find that this plays some practical role in things. So you need to recognize how high these tensions get as we try to make these things more and more horizontal. The lowest tension would be what? If we go back to the original problem, if we had them vertical like this with 4 kilonewtons, well, if I do this symmetrically, then this is just going to have 2 kilonewtons, and this is 2 kilonewtons. So that's the lowest we can get. And so each cable would only have to handle 2 kilonewtons. So when they're vertical, we have the lowest tension, and when as they're more and more horizontal, that's when we have the greatest tension. Okay, so do this problem. Very similarly, I want you to take free body diagram of that node right there. And again, we have 3 cables here. I've got 1 cable, another cable, another cable. I think you can see what that is. That's going to be 10 kilonewtons. I'll give you that one, and you know that already. So that's an easy one to get. I want you to figure out the other 2. It's same problem, but slightly different picture. Okay, so the answer, so what do we do now? We get this free body diagram. Notice that now this is going upward to the left, this is going downward to the right, and that's going downward. So when I do my conversion to this, what do I have? I've got, for this one, upward to the left, sine and cosine for the y and x. And now this one is downward to the right. Again, sine and cosine. So I work with this, and now when I take the sum of the forces in the y direction equals 0, again I use these to put into my equation. When I do the x, I use these. Again, I get 2 equations, 2 unknowns, and I can solve for this. Looks like that. So my end result is this. All right, this actually is a homework problem. So now this is a little bit different, and now notice we don't have 3 cables. We have we have one cable. So I have these pulleys here, and the cable goes like that. And now it's holding up 30 kips. So I want you to think about this problem. I'm going to show you how to do it, but I want you to draw a free body diagram here that make the cuts and determine the tension in this cable. Okay, so pause the video and do this. Okay, so this is, now what do I do? Now I take my free body diagram is going to be around here. And I look at, again, I'm going to do a copy and paste. And again, you have to be true to this. Copy, paste. What do I get? Well, that's what I get. And where have I made my cuts? Well, I made a cut here, I made a cut there, I made a cut there, made a cut there. So the method is I have to put a force or forces everywhere I made a cut. Well, it's one cable, so I do not use TAB, TBC, or TAD or TAE or whatever, because it's one cable. It's one cable, then I just use T. So I would end up with, you know, T, 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 and that gives me the free body diagram to work with. So now I end up with this free body diagram. I have to put in the 30 kip load, so I put the 30 kips there, but these are all just T, so it ends up to be quite simple. 1, 2, 3, whoops. 1, 2, 3, 4 T's. So I get 4T going up, I have minus 30 going down. Very simple to solve for this. T is equal to 7.5 kips. So it's all about the free body diagram here that we're drawing. Okay, so you do this one. Find the cable tension. Okay, pause the video here and do this one. Well, again, it's pretty similar to the other one. I take my, I'll do my copy and paste here. And again, where do I made cuts. So I have my, again, it's just 1 T, T, T. So again, I get 4T. So looks like this. And I get 4T minus 20. Got to put in the 20. I get T is equal to 5 kips. Okay, this is a little bit more complicated, but I want you to give it a shot. I now have, notice I've got 2 cables here. I've got one that wraps around like this. So it's a little bit different wrapping system. I have another one that wraps around like this. So I have 2 cables. I want to know what this force F is, which of course is going to be what the tension in this cable is going to be. So draw your free body diagram from this and solve it. So pause the video here. Okay, So let's start with the obvious, okay? The tension in this cable is obviously 20 kips, right? Because I just take this free body diagram, and I have the 20 kips going down, and I have to have 20 kips going up. So that means that, and this is, oops, why don't I just say this is, I'll call this T1, this one T2. So this is T2, and we can see very clearly that T2 equals 20 kips. So we'll keep that. You should be able to identify that pretty straight away. So T2 is 20 kips. So now I'm going to take this free body diagram down here. I'm going to take the 95 kips. Looks like that. And again, I can do the copy and paste, but we've seen it enough times we end up with that. And what do I know? Well, these are 20 kips. Those two are 20 kips. So I put on those two 20 kips. This is going to be my T1, or I just called it T at this point. And I show the 95 kips, of course. And I just use this. So I have what? I have T plus T, 20 plus 20, minus 95 equals 0. I get T is equal to 27.5 kips, which means that this F is going to be 27.5 kips. So you just need to, again, draw the different free body diagrams. So hopefully with the truss experience that you've had, you will be able to do these different free body diagrams and analyze them, be true to your free body diagram, and work from it. Okay, try another one. Try this one. Now notice, what do we have? I've got one cable that wraps around like that. Another cable AC. Another cable BC. Sort of combining both of those things. So you have angles here that you can work with. Make sure that when you do your calculation, you use with respect to the x-axis. Make sure your angles are with respect to the x-axis. Okay, so pause the video and find the tensions in each of those three cables. So CD is this one. Okay, so we can start with this. We've done this enough times now. You should be able to get it. So for that one, I'm cutting through 6 cables here. So I end up with 6 TCD minus the 25 equals 0. And so I get TCD is 4.17. Then what do? Then I look at this point here, and so it becomes, I have 4.17 on that one. It's at 30 degrees. Now we have to make sure we get our angles correct. If I use this as a right triangle here, then that angle there is 70 degrees. That angle there is 45 degrees. So I can, and again, so I get this free body diagram here. And so 30 degrees, 70 degrees, 45 degrees. Now everything's with respect to the x-axis, so I can use my sine and cosine. So this is upward to the left. Upward to the left, sine and cosine of 45 degrees. Downward to the left, downward to the left, sine and cosine of 70 degrees. Upward to the right, sine and cosine of 30 degrees. I now look at this, I take my y values, that's these. I put it into the sum of the forces in the y direction. I use these for the sum of the forces in the x direction. I now again have two equations, two unknowns. Solve for it. I get TBC is 4.44, TAC is 2.97 kips. Okay, here's a little bit of a different one. And I guess I'm going to use this as a homework also because I want you to think about this one. It's a little bit trickier. And so I want you to give it a shot. But I want to point out what we have here. So I have, I've got a cable here, a cable here, a cable here, and then I've got this cable at the top. And I got to apply an F to hold this up, to hold this 800 pounds. And notice, so this becomes a little bit trickier because if you make a cut here, notice the tensions are not the same. So in other words, that's one tension in there, that's a different tension, that's a different tension. They're all different. So when if I take a free body diagram about this point, I don't have, it's not, just to let you know, it's not T, 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 because they're all different. So anyway, I want you to think about it, see if you can figure out the complication, maybe you'll do something. So give it a shot, draw some free body diagrams, and see if you can come up with something for this one. Okay, how do we do this? Well, it becomes a little more complicated, but as I said, my free body diagram of this is now what? I've got my TA, TB, and TC, 800 pounds going down. Well, I can't solve this. I can't look at this and solve it because there are too many unknowns. There are three unknowns. I only have one equation here to use, which is the sum of the forces in the y direction equals 0. So I cannot solve that. So I have to start looking at some other free body diagrams here, like this one. Now, and so if I look at this, let's look at that one right there. Well, I've got, so I'm looking at, notice F is the force, it's got to be the force in that cable, right? So F and TA are the same. So if I look at this, I have what? I have the TAs going down, and I have I have TB going up. And over here, let me just erase that here. So over here, so for the next one, then what do I have? I have, I've got another free body diagram for this one. It's going to look like that. Well, what does it have? It's got TB going down and then TC going up. And I can do this one, and I have TC going down and TD going up. So it looks like I have, again, too many unknowns. I've got all these, I've got 4 free body diagrams here. How can I connect them together? Well, it ends up that here's how we can do it. So I look at this one, And what do I see? I see that I have, I take the sum of the forces in the y direction equals 0 here, which means that what? I have TB minus 2TA equals 0. That tells me, that's the sum of the forces in the y direction for that free body diagram. That tells me that TB is equal to 2 times TA. Then I look at this one, I do something similar, same conclusion now, but it's with TB and TC. TC is equal to 2TB. Well, what can I do with that? I can take 2TA, put it into my TB, and when I do that, I'm going to find that TC then is equal to 4 times TA. Now I look at this one, and again, what do I get? I get 2TC is equal to TD. I can put in, for TC, what do I put in? 2TB. And for TB, I put in 4TA. And so I get that TD is equal to 8 times TA. I go now to this free body diagram, and that tells me what? That tells me that TA plus TB plus TC is equal to 800 essentially. So, but I want you to draw it out this way, and then I can make some substitutions here, and I put in 2TA for TB, I put in 4TA for TC, and now the only variable in this expression is TA, and I get 7TA is equal to 800. TA is 114 pounds. And that gives me this F, and then I can figure out all the other tensions from that. Okay, we're going to pause there.